Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, we have learned differentiability and we started solving some problems on differentiability. In this session, we are going to solve some more problems on it. Let's get in. Consider the first problem. Check the differentiability of the function f of x equal to mod x plus mod of x minus 1 at x equal to 0 and x equal to 1. This function looks slightly difficult to deal with, so first I try to simplify that function and later we shall find out whether it is differentiable at x equal to 0 and x equal to 1. The mod x is defined as minus x whenever x is less than 0 and equal to x when x is greater than or equal to 0. Similarly, the mod x minus 1 is defined as x minus 1 when x is greater than or equal to 1 and minus of x minus 1 when x is less than 1. So let me divide it into three cases. When x is less than 0, when x lies between 0 and 1 and when x is greater than 1. And let us check what is this function defined at 0 and 1. So first, if x is less than 0, if x is less than 0, this function will be equal to f of x equal to minus x, and if x is less than 0, it will be less than 1. Therefore, this will be equal to minus of x minus 1. So I get here 1 minus 2x. Now for x equal to 0, the function is defined as mod 0 is 0, so mod of minus 1 will be equal to 1. So 0 plus 1 is equal to 1. Now consider in this interval, if 0 less than x less than 1. Now let me check this function. Since x is greater than 0, mod x will be equal to x, but x is still less than 1, so this will be equal to minus of x minus 1. Minus of x minus 1. So I get here 1. Now let me check the value of this function at x equal to 1. If x is equal to 1, then f of x is defined as mod 1 is 1 plus 1 minus 1 will be equal to 0. So I get here 1. Finally, we shall check what is this function for x greater than 1. If x is greater than 1, then f of x will be equal to, if x is greater than 1, then x is definitely greater than 0, so mod x will be equal to x plus, for x greater than 1, this is defined as x minus 1, so I get 2x minus 1. Okay. Let me write this as a piecewise function. So f of x is equal to, I have three definition for f of x here. For x less than 0, 1 minus 2x, 1 minus 2x if x is less than 0. If x equal to 0, x equal to 1 and x between 0 and 1, f of x is defined as 1. So this is equal to 1 if 0 less than or equal to x less than or equal to 1. And finally, for x greater than 1, it is defined as 2x minus 1. So 2x minus 1 if x is greater than 1. Now it is easy to check the differentiability at x equal to 0 and at x equal to 1. First, let us check the differentiability at x equal to 0. To check differentiability at x equal to 0, first I consider the left hand derivative L of f dash of 0, which is defined as limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 minus. I substitute x equal to 0 minus h and take limit as h tends to 0. This is equal to limit of f of 0 minus h minus f of 0 whole divided by 0 minus h minus 0 as h tends to 0. And this is equal to limit of, for any value less than 0, the function is defined as 1 minus 2x. So this is equal to 1 minus 2 into minus h minus f of 0 is defined as 1 minus 1 whole divided by minus h as h tends to 0. Now 1 and 1 gets cancelled. Here minus h and minus h gets cancelled. So I get here minus 2. So the left hand derivative at 0 is equal to minus 2. Now find out the right hand derivative, r of f dash of 0. This is defined as limit of f of x minus f of 0 whole divided by x minus 0 as x tends to 0 plus. Again I substitute x equal to 0 plus h. This will be equal to f of 0 plus h minus f of 0 whole divided by 0 plus h minus 0 as h tends to 0. So now h is greater than 0. So f of h is defined as 1. This will be equal to 1 minus f of 0 is 1 divided by h as h tends to 0. 1 minus 1 is 0, so limit of 0 will be equal to 0. Since left hand derivative, which is equal to minus 2, is not equal to 0, which is right hand derivative, the function is not differentiable at x equal to 0. Since L of f dash of 0 is not equal to r of f dash of 0, f of x is not differentiable at x equal to 0. Similarly, if I check the differentiability at x equal to 1, I get left hand derivative as 0, right hand derivative as 2. Since left hand derivative and right hand derivative are not equal at x equal to 1, f of x is not differentiable at x equal to 1. So this function is not differentiable at x equal to 0 and x equal to 1. Okay. We have seen that the function defined by mod x plus mod x minus 1 is not differentiable at x equal to 0 and at x equal to 1. Similarly, I can show that this function defined by sin x is differentiable at x equal to 0. Now let us try to understand this geometrically. So what I am going to do is, let us plot these two functions using maxima. First, let me plot this function. Define this function f of x colon equal is equal to absolute value of x plus absolute value of x minus 1 semicolon, and plot 2D of f of x in the interval minus 2 comma 2. I get a graph like this. Similarly, we shall try to plot this function in maxima on Android. First, define this function sin x f of x colon equal to sin of x, and plot this function in the interval minus 1 comma 1 using this command. I get a graph like this. Now if you look at these two graphs, the graph of this function in the interval minus 2 comma 2 and the graph of this function in the interval minus 1 comma 1, at x equal to 0 and at x equal to 1 we have a sharp edge for this graph, but for this graph at x equal to 0 it is smooth. What I am trying to explain is, if a function is not differentiable at a point, then we have a sharp edge at that point. If it is differentiable at that point, that function will be smooth at that point. That's why we use the word smooth function to define a function which is differentiable in the domain. Okay. Now let us consider the next problem. Check the differentiability of the function f of x defined by x into e power 1 by x minus 1 divided by e power 1 by x plus 1 when x is not equal to 0, and f of x is equal to 0 when x equal to 0 at x equal to 0. First, let us find out the left hand derivative at x equal to 0. L of f dash of 0 is defined as limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 minus. When I substitute x equal to 0 minus h, I get here limit of f of 0 minus h minus f of 0 divided by 0 minus h minus 0 as h tends to 0. By the definition of f of x, for any value not equal to 0, the function is defined as this. So I get here f of minus h is equal to minus h into e power minus 1 by h minus 1 divided by e power minus 1 by h plus 1 minus f of 0 is equal to 0 whole divided by minus h. First, these two terms will be cancelled. Next, as h tends to 0, I get here e power minus 1 by 0, which is minus infinity. E power minus infinity is 0, so 0 minus 1 and 0 plus 1 will be equal to minus 1. Similarly, let us find out the right hand derivative, which is r of f dash of 0 defined by limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 plus. This will be equal to limit of f of 0 plus h minus f of 0 divided by 0 plus h minus 0 as h tends to 0. When I substitute this, I get here limit of h into e power 1 by h minus 1 divided by e power 1 by h plus 1 minus 0 divided by h. Here h and h gets cancelled. Before taking limit as h tends to 0, I take e power 1 by h as common. E power 1 by h into 1 minus 1 by e power 1 by h. Similarly, in the denominator, e power 1 by h into 1 plus 1 by e power 1 by h. Here these two terms gets cancelled. As h tends to 0, e power 1 by h will be equal to e power infinity, which is infinity. So 1 by infinity is 0. So 1 by 1 is equal to 1. So we have shown that L of f dash of 0 is equal to minus 1 and R of f dash of 0 is equal to 1. They are not equal. So since L of f dash of 0 is not equal to R of f dash of 0, f of x is not differentiable at x equal to 0. Okay. Consider one more problem. Show that the function f of x defined by x into tan inverse of 1 by x when x is not equal to 0 and equal to 0 when x is equal to 0 is continuous at x equal to 0 but not differentiable at x equal to 0. First, let us show that f of x is continuous at x equal to 0. Okay. First, consider limit of f of x as x tends to 0. This will be equal to limit of x into tan inverse of 1 by x as x tends to 0. As x tends to 0, we get here 0 into tan inverse of infinity, which is pi by 2. So 0 into pi by 2 will be equal to 0. Since limit of f of x as x tends to 0 is equal to 0 and which is same as the value of this function at x equal to 0, we have f of x is continuous at x equal to 0. Now let us check the differentiability at x equal to 0. First, let me find out the left hand derivative. The left hand derivative L of f dash of 0 is defined as limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 minus. Substitute x equal to 0 minus h and take limit as h tends to 0. So I get here f of 0 minus h minus f of 0 divided by minus h as limit as h tends to 0. By the definition of f of x, this will be equal to minus h into tan inverse of 1 by minus h divided by minus h as h tends to 0. Here minus h and minus h gets cancelled. We know that tan inverse of minus 1 by h is equal to minus of tan inverse of 1 by h. As h tends to 0, I get here minus of tan inverse of infinity, which is equal to minus pi by 2. Now let us find out the right hand derivative. The right hand derivative r of f dash of 0 is defined as limit of f of x minus f of 0 divided by x minus 0 as x tends to 0 plus. First I put x equal to 0 plus h and take limit as h tends to 0. So this will be equal to limit of f of 0 plus h minus f of 0 divided by h as h tends to 0. By the definition of f of x, this will be equal to limit of h into tan inverse of 1 by h divided by h as h tends to 0. Here h and h gets cancelled. As h tends to 0, this will be infinity, so tan inverse of infinity will be equal to pi by 2. Here I am getting that left hand derivative at x equal to 0 is minus pi by 2, the right hand derivative at x equal to 0 is pi by 2. They are not equal, so f of x is not differentiable at x equal to 0. Since L of f dash of 0 is not equal to R of f dash of 0, f of x is not differentiable at x equal to 0. So the given function is continuous at x equal to 0 but not differentiable at x equal to 0.